So let's talk about an application for graph neural networks and a different architecture for graph neural networks, which we call it GNNVis. Of course, this one is inspired by graph attention networks. So it's just a variation of graph attention networks, but we use it for visualizing large-scale data. As you know, there are two methods or two paradigms for visualization. One is non-parametric, the other one is parametric. And the non-parametric methods like principal component analysis, I've explained this. I've explained all of them in my book, which is published in Springer, and I've used it for financial markets, algorithmic trading, in order to reduce the dimensionality and to have a better algorithmic trading based on these dimension reduction methods. And the linear discriminant analysis, I've explained it in my playlist for dimension reduction. Another one is multidimensional scaling, very popular. I've explained local linear embedding in my playlist for dimension reduction. I have explained it, TSNE and modified TSNE as well in another playlist, dimension reduction. But I haven't explained these. Of course, they are the same, like TSNE. They are used for visualizing large-scale data. And the data visualization, if you combine just the graph neural network with the problem of visualization, for example, using a TSNE loss, then so if you just combine TSNE loss, if you just combine it with any graph neural network such as GNNVis, which is also like graph attention network, then you can visualize really large dimensional data. And a major challenge for a non-parametric approach is that they cannot really handle the unseen data. There is a category, they call it inductive and transductive. You can learn about these things. So we cannot handle unseen data because they are out of sample. So of course you can do it, but you should rerun it again, the algorithm, because you cannot just use these unsupervised learning methods for out of samples. And to obtain a low-dimensional embedding of unseen data, it has to execute the whole learning process based on the overall set. So TSNE, of course, non-parametric TSNE, gives no function for embedding out-of-sample data in a low-dimensional space. And consequently, all the usual machine learning notions about out-of-sample performance are out. So if you see here, it is A and B are refers to for the training, for the GNNVs, and also for visualization. As you see, there is you see stability. This one is almost here. This one is almost here. But for the other one, which is another algorithm, LargeVis, for example, this one is here while this one is here, so it is not stable. So here it is unstable, it's crash. So it cannot handle out of data, but here it can handle out of sample distribution without any problem. But the GNN are resource consuming in the training stage, of course. In the training stage, they take time, they take lots of time, but in the inference or in the visualization of unseen data, it is very quick in contrast to older methods. So we partition the large graph into dense subgraphs, and then we use subgraph-based negative sampling. I've explained what is negative sampling in my playlist for natural language processing. And GNNVis is, you can see it as a parametric model. And you have a high dimensional representation as usual. You want to map it to a low dimensional representation Y. So S is less than D. D is high dimensional. And the goal is to just preserve similarities of our pairs. You can watch my playlist for metric embedding to see what is distortion and what do I mean by preserving these things, these similarities. And GNNVis is based on graph attention network, so I will explain GAT because it is based on that with a very, very similar change, with a very small change. So there are 4 components that I should explain. First of all, you should create your graph if you don't have it, or if you can't do it as simple as people in Pinterest company. And the next one is graph attention based feature fusion, which I explain what are what kind of architecture is this, because we have lots of graph neural networks, so it's a special kind of that. And then for any graph neural network, you should have a loss. What is your loss? If it is a classification, what kind of loss? You could use any kind of loss, for example, cross entropy, any kind of loss. And the inference stage is the visualization stage, because now we can infer, we can put an out-of-sample distribution and see what happens. And the graph attention networks, so this article is for ICLR2 sample by great people like Yashua Bengio. And so the key idea is to compute the hidden representation of each node by just attending to its neighbors. And this is called attention, and this is the article. And here I can explain it. For example, this node 1 has more attention to 2 rather than in comparison to 3. So, and we use Leaky Relu. The difference between Relu and Leaky Relu is here. And here we have 2 types of parameters. One is W, the other one is A. So both of them should be learned. And this pi, double pi, is just a concatenation. You shouldn't forget that this is just concatenation. And so we are just using weighted average of these embedding to see, to update, in order to update for the neighbors. So for all of the neighbors of V, you should add them. And but we should normalize it. That's why we use softmax. And the other things, instead of any nonlinear activation, they use Leaky Relu. And here we call it case attention, because you could have a multi-headed attention just for scalability, and also for semantic meanings. For example, your attention could be, for example, you attend to the age of a person. That is one head. Another head is the EQ of a person. This is another head. So for 2 reasons, we use multi-head attention, as I explained in the transformer model in NLP. And in my playlist for deep learning projects, I explained what is transformer. So graph neural networks are just transformers. They are just represented in a different way. And so it's an alternative to transformer. Of course, they are dual to each other. And so you are learning by using these weights. So I said there are 2 kinds of weights: this W, which is shared, and the A. So learning them, you can obtain your representation. And finally, because you are, the dimensionality is changing first. So you should first do averaging and then use this nonlinearity. And just like TSNE that I explained in lecture 10, I think, of my playlist for machine learning ideas. So as I explained, I showed you that this is the pairwise similarity in TSNE. So you can do the same thing, but now things are on the graph. So it's a graph neural networks. But in order to learn the parameters, you need the laws, and you just pick these laws, the KL divergence between the actual probability and the approximation. And the visualizing stage, in this article, which is written by those great Chinese researchers, so they used the combination of random projection trees, which is of order of complexity n log n, and the nearest neighbor descent. So of course they use both of them, first this and then this. And this is just the summary of what I said, what I've just told you. And you can compare for training stage and visualization stage for both MNIST and FMNIST. You can the training time, as you see, the training time is huge, 600 milliseconds, 600 seconds. But the good thing is that for visualization stage, it is much smaller than, for example, MTSNE, 36 and 389. So it's quite an improvement for out-of-sample inference and testing time. And Feynman technique, my favorite physicist is Richard Feynman because of his methodology for research. It's like my methodology. So just pick and study a topic that you love and explain to someone. For example, I explained to my niece, she's just 4 years old, but I try to explain it. But 6 years old are better, they understand much more. But identify the gaps. For example, in what places you are hesitant, you don't know exactly if you have understood that or not. And then you go to literature, you read the article again, and you read alternative articles, you understand it. Step 5, I suggest that you should implement it, because if you implement it in Python or Java, so you understand each step, you touch each step of the algorithm. And in the last step, just give a lecture in YouTube. Give a lecture in YouTube because you never forget your own lecture. You never forget it because you have explained it with those slides, beautiful slides, and so you never forget it. And that's it for second lecture for graph neural networks.